Good morning, everybody. So welcome back. I hope you all had a great Thanksgiving break until Saturday, that is. That was pretty terrible. But hope you had a great Thursday and Friday. And at least the Browns were able to beat Tom Brady, so at least we get a tiny little victory. But anyways, getting back into chapter 10. I do say, though, whenever the Buckeyes lose, it's a great time to study. So I think this weekend, great opportunity to focus on chemistry or some other football teams losing. So I don't know. Maybe we still have football to watch. Okay, so getting back into chapter 10, we were trying to understand some different theories of how gases behave. That's where the kinetic molecular theory of gases was coming up. So the kinetic molecular theory of gases was showing us that a gas sample has a wide distribution of velocities. And so you can see, even at 0 degrees C for a given gas, you have some particles that travel slow, some particles travel a little faster, and some traveling very fast within a gas sample. So we get a unequal distribution. This isn't a perfect like Gaussian or bell shape. You have more particles that are on the faster side so that your average point is off of the most probable point. So our most probable is the highest point. That's the fraction of molecules that have the highest velocity. And then our average, or our root mean square point. So that root mean square average is a little bit off center, a little bit faster than that most probable point. So those points are kind of pointed out over here. So our most probable, the fraction with the greatest speed, the average, just the simple average of the distribution, and then the root mean square is just the velocity related to the average kinetic energy. And so as we start thinking of average kinetic energy, if a given gas at a particular temperature has so much energy to distribute, if we raise the temperature, we have more energy to distribute, therefore faster velocities. So we see if you increase the temperature to 100 degrees, you don't shift the velocities higher, but you on average make the velocities higher. So you still have some slow particles, but then you have some even faster particles, and you have a greater fraction traveling faster. And then that does kind of pull the fraction at each of your velocities down a little bit because we're stretching out our velocities. So the area under the curve is just equal to the population of molecules. And so for 100 degrees C, we just have on average faster moving particles. So the most probable point is higher, the average point's higher, and the root mean square average is higher than at 0 degrees. And so then we briefly had showed this slide. I don't think we talked too much about this. If you think about kinetic energy being 1/2 mv squared, and if kinetic energy is just basically related to the temperature that the gas sample's at, so at a given temperature, the sample of a gas has the same kinetic energy to distribute. So then if you have a more massive particle with the same kinetic energy, it has to travel with a lower velocity. So you can look at a given gas sample and see that the lighter particle, hydrogen, has the highest velocity of the gases on this slide. So the average, most probable, all those points for hydrogen are going to be higher because you're talking hydrogen being 2 AMU per particle. Helium is about 4 AMU. So a little bit more massive for helium means that if it has a higher mass, then it has to have a lower velocity on average. So the velocity distribution for helium is lower than hydrogen. If you go to water, about 18 AMU per particle, that its distribution is even slower. Nitrogen, even slower at 28 AMU. And of the gases on this slide, 32 AMU. For oxygen, it has the lowest set of velocities. So the distribution of velocities goes slower, the heavier the particle, and it goes faster, the lighter the particle. We had seen a couple of equations. I'll rewrite them here for the root mean square velocity. The root mean square velocity would be equal to the square root of 3 RT divided by the molar mass. And then our most probable point is equal to the square root of 2 RT divided by molar mass. So we have to talk a little bit about how we actually plug numbers into this equation to get velocities out, but we'll talk about that on the next slide. But these are basically the same equations other than 3 RT versus 2 RT for the most probable velocity. Now, one of the other things you see here is you can sort of see that if you go to a higher molar mass, then you're going to go to a lower velocity. So you get the same, you can see it with the equation plugged in here, that we're going to a lower velocity on average, the heavier the particle. And then also you can see that if we were to increase the temperature of a gas sample, so if we take the temperature and increase it, that's of course going to increase the average and the most probable and the root mean square velocities, as we would have expected. So temperature plays a role here. In the equation, we can kind of see the direct relationship between velocity and temperature. And so then, if we actually want to plug into these equations to solve for a velocity, just let's think about the gas constant R that we'd want to use. And so the ideal gas constant R, the one that we've used more predominantly, of course, is the 0.08206 liter atmosphere per mole Kelvin. The thing that we mentioned with this gas constant is that this is the non-SI unit version of R, or a version of R that doesn't use the SI units. And so if we start thinking velocities and an SI unit like meters per second, if we want to calculate a velocity in meters per second, that's SI units. You might think, okay, let's try to calculate or use R, but in the units of the SI units. And so if we try to use the idea, let's try to plug everything in for derivation of R in SI units. If you recall, when we got the liter atmosphere per mole Kelvin, was by taking 1 mole of a gas at STP, so at 0 degrees C, so 273.15 Kelvin, at 1 atm, that was the volume of 1 mole of gas. So when we were solving for this volume, or this units of R, you might have remembered that we were plugging into this equation here and then setting our pressure to 1 atm, standard pressure. We were multiplying the volume, which was 22.414 liters. Then we were dividing by, that was 1 mole of gas, and then at the temperature 273.15 Kelvin. That this was how we got the 0.08206 liter atmospheres per mole Kelvin. And so if you want to derive or rederive R in SI units, what we'd want to do is just say, well, what would the pressure of 1 atm be, but in like Pascal, which is the SI unit of pressure? So if we convert 1 atmosphere to Pascal, that would be 101.325 Pascal. So that's just 1 atm in Pascal. And then the liter is not exactly the SI unit. We might convert to cubic meters, which would be the SI units for volume. And so we might recall that 1 liter is 0.001 cubic meters. We could get that derivation a couple different ways. One, we could just look it up. Or two, we might just remember the connection between liters and cubic centimeters to milliliters, milliliters to liters. But this is just the conversion from liters over to cubic meters. And then this is still 1 mole of gas at 0 degrees C. So we haven't really changed anything other than we just converted the pressure to Pascal and then the volume to 22.414 liters over to cubic meters. And so then when we do the math, that works out to be 8.314, and then the units could be like liters, atmospheres per mole Kelvin, well, it'll be Pascal cubic meters per mole Kelvin. Well, if we inspect and kind of go back to what a Pascal is equal to, you might recall that a Pascal is a kilogram meter to the minus 1, second to the minus 2. And so then if that's what the Pascal is equal to, and we multiply this by cubic meters, and then we're dividing this by mole Kelvin, do you see how when we multiply by cubic meters that this becomes square meters? So kilograms meters squared per second squared. And then that just turns out to be a joule. And so the Pascal times cubic meters in units is equal to 1 joule, because they're both equal to a kilogram meter squared per second squared. But now, if you also remember Pascal's SI units, meters cubed SI units, joules an SI unit, that these all kind of tie together, so that these are the units of R using SI units. And so 8.314 joules per mole Kelvin is just a different set of units for the gas constant. And it's really not a set of, these units of R aren't really useful for other problems to this point in chapter 10. But when we're trying to solve for a velocity in meters per second, we're going to need to use this version for R if we're plugging into that square root of like 3RT divided by molar mass. So let's look at one of those where we actually plug in and try to solve, for the root mean square velocity for the gas particles in a hydrogen sample at 25 degrees C. In a way, this is an easy problem as long as we know what units to plug everything into. And the way we'll know what units to plug into this equation is just to sort of think about the units and write them out as we go. So if our root mean square velocity equation is 3 times RT divided by molar mass, and we want to get this out in meters per second, which is an SI unit, that kind of clues us in that we probably don't want to use liter atmospheres per mole Kelvin because I don't see meters per second in liter atmospheres, but I can see them within joules per mole Kelvin or Pascal cubic meter per mole Kelvin. So if I start plugging into this equation here, I'm going to take the square root of 3, I'm going to use the 8.314 joules per mole Kelvin. Then we multiply by the temperature. Of course, it has to go to Kelvin. Everything in this chapter is going to Kelvin, so that's 298 Kelvin. And then the molar mass is the next unit we have to think about what unit we want to put it into. Well, what's the SI unit of mass? Is it the gram or kilogram? It's the kilogram. So if you think SI units, you might think, okay, we got to go kilograms per mole for our molar mass. And so hydrogen is 2.016 grams per mole. So that would be 0.002016 kilograms per mole. Now, of course, you're going to be wondering, well, how do I know for sure it needs to be in kilograms per mole and not grams per mole? Well, we just have to think about what the joule is again. So a joule is 1 kilogram meters squared per second squared. And so that's where we see the meters and seconds coming out in the problem and the kilogram. So we need our molar mass in kilograms to cancel into the units of joules, being a kilogram meter squared per second squared. So let me actually rewrite this here and actually rewrite the units of joule in here as kilogram meter squared per second squared. So that's how we see we want to go to kilograms to cancel kilograms, Kelvin to cancel Kelvin, the mole unit cancels, and the only thing not canceling is meters squared per second squared, and we're taking the square root. So when we take the square root of the units, we get meters per second. All right, let me give you guys a second to calculate this out and to maybe think again about the units if you need to and come up with the answer, and we'll spend about a minute, then move on. All right, so probably you guys got this. I mean, it's pretty easy once you have the calculation right now, but just think everything is in SI units here. So from the units of R to temperature and the molar mass, kilograms per mole. And so that works out to be 1920 meters per second. And so with an equation like this, you could work out and calculate the average, or in this case, the root mean square velocity for a hydrogen sample. You could do other gases, you just have to know the molar mass. And then we could also calculate the most probable by 2RT divided by molar mass if we wanted the most probable. If we saw this on a test, I'm pretty sure they'd give you this equation. I think they'll give us the gas constants. I mean, we'll see the info sheet when it comes out, but I think the units of R, we'll have both units of R on our equation sheet, the 8.314 and the 0.08206. The temperature to Kelvin conversion is usually given, but hopefully we do that enough that that's not a sticking point. And the main thing you need to know, just through working at the units, is that the molar mass goes kilograms per mole.
From units going back to the first flight path, I thought the 0 degrees had larger volume and area below the graph than the 100 degrees, which I thought would be reversed. I should be.
Okay, so the 0 versus the 100, the lowering of the curve, you mean? So the lowering of the curve is just from the fact that we're not just shifting, we're not just taking the 0 degree curve and shifting it over, that we still have peaks. Like notice that you still have fractions of molecules that are traveling slow. And then we are sort of stretching out the velocities that are traveling fast. And so the area under the curves for the blue and the red have to equal each other. So if you integrate under the curve, you have to get the same number. You have to have the same number of molecules. And so if you're just imagining you have, say, 1% traveling at the most probable point, by stretching out the velocities, you're going to have like less than 1% at 100 degrees C. So that's why you're lowering the curve. Is
number of particles, I get it, but if you take the speed, then the area should be different, because with 100 degrees, then they should be traveling at a different speed. Number of particles, I get it.
Yeah, I'm not sure why we just, maybe we'll just talk after class, but I think, you're just looking at the fraction of molecules. You get a lower fraction at 100 degrees C at the most probable point just because you're stretching out all the velocities. Right.
But the lower axis is molecular speed, so speed and the fractions that multiply the area of the air.
Well, that's not how you would integrate under the curve from like the 0 to infinity. I mean, it becomes a calculus problem more than a chemistry problem at that point. But the speeds themselves, like you wouldn't multiply the fractions by the speed. You would just like count under the curve. Like you would almost, say, well, what's the area here? You have to extend out to get the full area. That the area under that curve has to be equal to the area under the blue curve. Okay, and so, yes? Okay, I was trying to put the slides so they'd be in order. Anytime I have to go back to a slide, the audio doesn't realize that I went back to the slide later. So, no, it's fine. There's two more sections in the text. One of them is on effusion and diffusion, sort of on the rates of gases as they escape from a pinhole. So in this cell here, there's a tiny little pinhole from which the gas particles can escape. You can think about a hole on a tire or something along those lines for how fast does it take a gas to escape from the pinhole. And you can compare there being perhaps two different types of particles in the gas mixture. And so if we're looking at, say, a second particle where the second particle is heavier, so we have a second particle here that's heavier, the heavier particle on average is going to have a slower velocity, so it's going to be traveling slower. And you might think, well, how often are the heavier blue peaks going to hit the pinhole versus the smaller, faster red peaks or the red molecules? So the red particles are going to travel faster, and they're going to be hitting that pinhole more frequently. So the rate at which these red particles hit the pinhole is going to be greater than the blue particles. And the rate at which the particles travel is just related to their molar masses. And so Graham's law of effusion says that the rate of escape of particle 1 compared to the rate of escape of particle 2 is just related to the inverse of their molar masses. And so the inverse of their molar masses is just coming from the fact that when you think about the velocity, that the rate of escape of a gas is proportional to its velocity, and the velocity is proportional to 3RT divided by molar mass, so it's proportional to the inverse of the molar mass. And so the rate of escape of particle 1 versus particle 2 is related to the inverse of their molar masses and the square root of those molar masses. And so now, if you think about, like, if you forget about the equation for a minute, the lighter particle should escape faster. So the rate of escape of the lighter particle should be faster than the heavier particle because the lighter particles traveling faster are going to hit that pinhole more frequently. So if we're comparing the rate of escape of, let's say, hydrogen gas from the sample where particle 2 is oxygen gas, we would expect the rate of escape of hydrogen should be greater than oxygen. Let's see if that works out. So the molar mass of oxygen is the 2, so this would be the molar mass of oxygen, so 32 grams per mole, or 0.0032 kilograms per mole. And the rate of escape of particle 1 related to the molar mass of particle 1 is 0.002016 kilograms per mole. And so then we take the square root of those molar mass differences. So the 0.0032, you can see that that's going to be greater than 1. I mean, I can calculate this out. 0.0032 divided by 0.00, or it's 0.032, sorry. The 32 grams per mole to kilograms per mole is 0.032 kilograms per mole. So 0.032 divided by 0.002016 is 15.87. So the rate of escape of particle 1 of the H2 is going to be equal to 15.87 times the rate of escape of particle 2. The particle 2 is oxygen. So the rate of escape of hydrogen is about 16 times faster than that of oxygen, just due to the relationship of their molar masses. And so that helps kind of prove what we suspected, that the lighter particle travels faster, has a greater probability or rate of hitting that pinhole, it escapes faster through the cell. And so then if you have a question like this, which would diffuse the fastest from a tire with a small pinhole leak in it? We have oxygen, CO2, and nitrogen. And so really not a trick question. So 32 grams per mole, 44 grams per mole for CO2, 12 plus 32, and then 28 grams per mole for nitrogen. So the fastest is going to be the lighter particle. So the lighter particle here is nitrogen. And so then the CO2 would be the slowest. So the question asks which of the particles escapes the slowest from the pinhole would be the CO2. So the faster particle, so we want the particle to be fastest to be the one with the highest average velocity. And the thing that's really funny here with this question is, if you go to get your tires changed, a lot of times they'll try to upsell you on filling them with nitrogen, and they'll give you like a little pamphlet sometimes. I've gotten this before where it talks about the benefits of nitrogen in your tire, and one of them is that it escapes somehow slower than other gases. I'm thinking, well, the other gas is oxygen. Like if you talk about air, if you're putting nitrogen in your tire, instead of putting 78% nitrogen, 21% oxygen, if you're putting 100% nitrogen, you're actually removing a gas that if used is slower than nitrogen does by using 100% nitrogen. And then they also talk about how nitrogen's bigger, which doesn't make any sense either, because nitrogen's triple bond is actually smaller than oxygen being a double bond. It really makes no sense on why you would pay. I think that the charge last time I went in, they tried to upcharge me $15 per tire to fill it with nitrogen instead of just ordinary air. Like a gas cylinder of nitrogen costs about $8. They can probably fill 10 or 20 tires with. So definitely getting ripped off if you choose the nitrogen fill when you go get your tires changed. So if chemistry does anything for you, maybe it saves you a couple bucks when you get your tires changed.
But I thought it was non-reactive. That's why the rim reacts with oxygen or the other particles in the air. That's why they put nitrogen. That's what I thought.
Well, that's one of the other benefits too. And I usually say, well, how bad's the other side of the rim do? Usually not so bad. I don't know. So, the one thing you might want is dry air, if anything, and not necessarily it being nitrogen. You just, whatever gas you put in, not to have water. So it's really water that would cause the damage, not necessarily oxygen, or the presence of oxygen and water together. But I've never had a rim. I've never had to change a rim. Oh, you did? I guess that goes back to chapter 4 on corrosion or something, or maybe later in chapter 20 you come back to that topic. Okay, and so then the diffusion of gases, so effusion is escape from a pinhole. That's what we were just talking about. So this is the escape from a pinhole. The diffusion of gas is the smell from one side of the room making it to the other side of the room. If you think cooking, or like the smell of coffee being made downstairs, making its way upstairs. And so that's the diffusion of gas. So this is like the flow of gases together. So the a gas starts here, but then it has to flow through a medium that contains other gases. And so if we release a gas particle over here, in order for it to make it to this side of the room, it has to bounce off of air molecules to make it over there. So the particle is not just going to go in a straight line path, because on a straight line path, it's going to eventually hit like an oxygen or nitrogen particle, maybe hit off another particle into a different direction. So we release a whole slew of, like if we spray a perfume or something like that, we have a large fraction of molecules. They're going to be bouncing off in every different direction. And it might just take a little bit of time for them to make it through the medium, being air in this case, to the other side of the room. And so our mean free path is how long on average does a particle travel before it encounters another particle in the medium. And so the distance the particle travels on average before it encounters another molecule is our mean free path. And so this is how far it takes a molecule to travel before it strikes another particle. And so that mean free path can be increased. You want it to be longer if you want the particle to make it faster across the room. And so our mean free path is going to increase when a few things happen. So our mean free path is going to increase. So the longer the mean free path means the longer the particle is traveling before it hits another particle. This is going to be longer whenever our gas pressure that it's flowing through is lower. So that's the pressure of the medium. So that's like the pressure inside the box. So if we make the pressure inside the box lower, there's fewer gas particles that particle we're releasing is going to encounter. We might call this the medium, the pressure of the medium that it's flowing through is another way of saying that. It's like the pressure of the box. So if you make that pressure higher, more probable a particle is going to hit another particle that would lower the mean free path. If you want to increase the mean free path, you would lower that surrounding pressure. If you want to increase the mean free path, you might make the particles travel at a higher temperature. So if the temperature of the particles is higher, then they'll be traveling faster. So it gives them a greater chance to travel a longer distance before hitting another particle. And then you might make their molar mass smaller. So again, that would increase the velocity so anything you can do to increase the velocity of that gas that you're releasing into your medium, anything that increases the velocity of the gas should increase that mean free path. Yeah.
I thought heavy gases settle down and light gases go up.
Well, but if they're trapped in a box, they're going to be bouncing off the walls at a faster rate than gravity's pulling them down.
The heavy ones still will be lower, and the lighter ones will be above.
Well, not really. So that's not really. So in a gas cylinder, the gases are going to expand to fill the container, and so they're going to be just bouncing off the walls of the container. So their random motion is going to mix them, and the gravity's not going to let them settle. Yeah. So the lighter the molar mass, the faster a particle will travel. A weird topic, but like if you're designing a nerve gas, you make them lighter. So if you ever like read into like what substances are used like ridiculously in the case of war, a lot of times it's really light particles. So the lighter the particle, the faster it travels through a medium. The heavier the particle, the worse the nerve agent would be. But you can understand some different properties of nerve agents if you think about their relatively light molar masses. Okay. So then the last topic in the chapter deals with real versus ideal gases. So we've talked a lot about the ideal gas, which is the idea that the gas itself, that it has no attractive forces, and that the particles occupy a negligible volume of the container. That whenever these two assumptions are broken, then we have a breakdown in our ideal gas law. And so whenever particles begin to have attraction for themselves, then that's going to lead to a problem with our ideal gas law. And then also, whenever the particles begin to occupy an actual portion of the container, so the particles occupy the non-negligible volume is saying that the particles occupy such a small space in an ideal gas that we don't have to factor in how much of the space of a container is being occupied by particles. So once particles start to occupy a negligible portion of the container, once they actually start to take up a significant amount of space inside the container, we have to take into account how much space is being taken up by the particles. And so the finite volume problem leads to an issue with the ideal gas law, as does the case of attractive forces. Now, if you start thinking of what it would take for these two factors to be broken, it's almost two different set of conditions. Like the attractive forces, this is a low temperature problem. Why low temperature? Well, what happens if you reduce the temperature of a gas? At some point, the gas is going to liquefy. If you think of the few moments, so if you're picturing, say, water, you have water vapor, so you have a gas sample that's at a high temperature, so you're at a couple hundred degrees C, and you start lowering the temperature of that gas, you start getting close to 100 degrees C, say you're at 110 degrees C, you're going to start to get some condensation. You're going to start to get droplets forming within the gas mixture. If you're calculating pressure of the gas, so let's say you're using the ideal gas law and saying, well, how much gas is in the container? What's the temperature? What's the volume of the container? That the problem of particles impacts the ideal gas law right here. So if you have particles sticking together, like the apparent number of moles is not what you think it is. Like if you think you have, let's say, 10 moles of gas in a container, but at some moment, 2 moles of the gas are actually stuck together as a particle, and then the other 8 are free molecules, you really only have 9 moles of gas in that case. And so let's say the reality is, due to attractive forces, your apparent or your true number of moles, because some particles are sticking together, the actual number of moles of gas is lower than what we think it is from the ideal gas law. So this is how attractive forces gives us an error when we're calculating pressures using that ideal gas law. And so whenever the apparent number of moles begins to have a problem, it's going to be when we get close to the boiling point of the gas, so at lower temperatures. And then the finite volume problem comes whenever we just have a relatively high pressure. So if we have the case, we're just putting a tremendous number of particles into our container. So we have a container and we just like pressurize it, and we're trying to calculate the pressure using the ideal gas law. As we put more particles into a finite volume container, the particles inside that gas are going to take up a greater percentage of the container. And so where this is going to play a role is in the volume here. So we really want to plug in our free space volume. And so for our free space volume, if we were just basically saying before, well, the free space volume is basically the volume of the container, because at relatively low pressures, that's true, that the percentage of the space taken up by gas particles, if it's less than, say, 0.5% of the container, then it's not a correction we need to make. But if you go to a set of pressures with the ideal gas law, maybe you're going to calculate a pressure of a couple hundred atm, at that pressure, you're going to have a significant portion of the volume being occupied by the actual particles of the gas, and that's going to lead to an error in the volume part of our equation. We want to plug in the free space volume, and so if we plug in the true volume as the free space, we're going to see that we get a different pressure, and that the ideal gas law pressure is going to be skewed by using the gas law. And so what ends up happening is there's almost like two different problems. So at the low temperature, low pressure problem is the apparent number of moles being lower than we think. And so when we think of plugging in and solving for like pressure, so in this case here, our number of moles is lower in reality than what we think it is. So we're making an error that makes our pressure look like it's too high from where it should be. And then whenever we start pressurizing the gas, then we have a different problem where our volume now is lower than we think it is. And that makes our pressure then become smaller than we think it is. Then we have an error the other direction for our gas mixture. So we just have two different errors. We have an error from the attractive forces. We have an error we introduce from the free space volume. Now, there's an equation for this. That's the van der Waals equation, so we'll show how this gets used in a second. So our van der Waals equation what it tries to do is it tries to make the two corrections. The easy correction is the V minus NB. If you notice this equation, it looks like PV is equal to nRT. And so it's trying to fix the volume for the free space problem. It's trying to say, well, let's plug in the actual free space. Let's take the volume of our container and then subtract the number of moles times the sort of liters per volume that the actual gas particles occupy in the gas mixture. So if you look at the series of B values, that these are telling you the volume per mole that the gas occupies. And so, like, let's use neon as an example. And so you have 0.0171. So if you have 2 moles, let's say you have 2 moles of helium in a container, then the helium particles are going to occupy 2 times 0, so 2 moles. Let's write this out more clearly. So we'll have 2 moles of helium times 0.0171 liters per mole. And so the volume of the helium particles is 0.0342 liters. And so now if you have, so remember 2 moles of gas at STP would be 2 times 22.414. So this would be like this would be 44 liters at 1 ATM. And so just to give you a picture of like how big that volume is. And so then if we want to put this into even like a 10-liter container, that would have a relatively high pressure, but still the neon particles are going to occupy a really small portion of that container. But put this much neon into, say, a 250 milliliter container, now you can kind of see the problem, that the smaller we make the container, the greater the percentage of the space of that container is being occupied by the neon particles. And so if you take the volume of our container minus the space actually occupied by neon, then that tells you the free space. And so if we even go really small, we say, you know, if you're using a 100-liter container, almost free space, almost 100% free space, right? But if you're using a 100-milliliter container, so 0.1 liters, then our free space volume would be 0.0658 liters. So you can see that about a third of our space is taken up by the neon particles if we only have a 100 milliliter container. So if we want to calculate the pressure of a neon mixture in a really small container with a high pressure, then we are going to have to use an equation like this one here, like the van der Waals equation, to more accurately calculate the pressure. We're not going to be able to use the ideal gas law to get an accurate prediction of the pressure of that gas. Okay, so the minus NB is trying to say, well, that's the space occupied by however much gas is in the container. So minus NB is the space occupied by the particles. And then our volume of our container minus that volume is the free space volume. So this difference here is our free space volume. And then if the pressure, if we think about intermolecular forces, pressure is being lost when particles are sticking together. So if we can add the pressure back in by however many particles were stuck together, that can fix our pressure calculation due to intermolecular forces. So the part here is trying to work out our intermolecular forces, or attractive forces between our molecules. So IMFs are intermolecular forces. So as intermolecular forces increase, attractive forces increase. So intermolecular forces are just how attracted our molecules are together. So as our A value goes up, let's compare something like a noble gas has a really small A value, not really attracted to itself, but then water, which is polar, has that built-in charge in it, has a much greater attraction, has a much higher A value. So in some ways you can see that as the attractive forces increases, the A value increases. So A is just proportional to how strongly attracted a molecule is for itself. And then we're multiplying our N and V. Now this just ends up being the volume of our container. It's really interesting that you don't correct for the free space volume in this volume, that you just use the container volume. But I think that's because this equation was derived kind of using that volume and not the free space volume. So you correct for the free space for the volume, and then you just use the volume of your container, and then the number of moles squared times A. If you notice A has weird units, the units of A are liters squared ATM divided by mole squared. And so if you multiply this by mole squared, so you have N squared, so that leads to the mole unit canceling, and then you divide by volume squared, and that leads to the cancellation of the liter square units. And then we're just taking an ATM unit and adding it to the pressure. So this pressure here, we can think this is our ideal gas law pressure. And then we're correcting the pressure due to intermolecular forces. So we're trying to add back in the pressure that were lost by intermolecular forces, is what this problem here is trying to do. And so this is the, if you calculate N squared A divided by V squared, this is the pressure that's lost. This is lost pressure due to the intermolecular forces, due to the particles sticking together. So we're just trying to add that pressure back into the problem. And if you're trying to solve for the pressure, you're trying to subtract off that pressure. So if you're trying to solve for your pressure, then you're trying to subtract off the pressure that's being lost due to intermolecular forces. So we have two corrections being made in this equation. We have the intermolecular force correction proportional to A. A is proportional to strengths of intermolecular forces. So the bigger A is, the stronger the attractive force between the molecules and the gas mixture. And then the B value is the space occupied by molecules. We haven't talked too much about the range of B values, but if you compare, like as you get to a bigger gas particle, as you go to a more massive particle, tends to take up more space. The only weird one is helium. I've often thought that this has to be some kind of typo or just like there's something weird going on here, that helium actually has a higher A value than neon. But generally, if you go to a higher molar mass, you go to a bigger B value. If the particle is just bigger in volume, it takes up more space. So having more mass makes the particle take up more space per mole. And so B tends to increase with size of the particle. So A with intermolecular forces, B with size. Real quick. So for nitrogen, 1.39, 391. All right, so let's compare our pressures we would get for a nitrogen sample using the ideal gas law versus the van der Waals equation. And we'll do this for a nitrogen sample at 298 Kelvin. So we're using N2. I need my A and B values. Let me grab those. And then 0.0 liters per mole. Okay, so PV is equal to nRT for the ideal gas law. And so just to calculate the pressure we would get with the ideal gas law, we would take our 5.5 moles times our usual gas constant, 0.08206 liter atmosphere per mole Kelvin. It doesn't say to calculate the pressure in ATM, but that's the unit that's going to make sense to do this in. Let's calculate the pressure here in ATM. And that's just to make sure we see why we're using these units of R. It's because we want to get the pressure out in ATM. And then we multiply by the temperature. So 298 Kelvin. And the volume of the container is 600 milliliters, so 0.6 liters. So this looks like it'll be a high pressure. Yep, 224 ATM. Okay, so the ideal gas law is making two mistakes here. One, this is a high pressure, so we probably have the nitrogen molecules taking up a large portion of this container. So this is likely an error here. And then we might have some particles stuck together, so we might be able to sort of correct for that, the particles that are sticking together here as well. So if we rewrite the equation from the previous slide, it was P plus N squared A divided by V squared. And this is always a given. We wouldn't expect you to memorize this equation. V minus NB. So PV is equal to nRT. So we're just correcting pressure and correcting volume. So this here is the pressure we want to solve for. I wrote before that this was the ideal gas law pressure. I think this here is the ideal gas law pressure. So P plus N squared A divided by V squared is equal to kind of our ideal gas law pressure. And then this pressure here is our van der Waals pressure. And the van der Waals pressure is just the more accurate calculation of the pressure. So this here would be our van der Waals pressure to kind of compare it to the ideal gas law pressure. Like the PV is equal to nRT gives us the pressure following the ideal gas law, and solving for pressure from the van der Waals equation gives us the van der Waals pressure, and then the van der Waals pressure is just going to be a more accurate prediction of the pressure of the true gas sample under these conditions. And so then if I want to solve for pressure, I need to divide both sides by V minus NB. And then I need to subtract N squared A divided by V squared. Let's get rid of that on this side. So just doing the algebra to solve for van der Waals pressure. So the van der Waals pressure should be equal to nRT divided by V minus NB, and then minus N squared A divided by V squared. Okay, and so then plugging in for moles, every time we have N, this is just our 5.5 moles. Our V's are the volume of our container. So this is the 0.600 liters. Then our A and B units are plugged in. The ideal gas law, the 0.08206 liter atmosphere per mole Kelvin, and then 298 Kelvin. Okay, so let's try to calculate this kind of in chunks. So our van der Waals pressure will be 5.50 moles times 0.08206 liter atmospheres per mole Kelvin. We're at 298 Kelvin. So our volume is 0.6 liters minus 5.50 moles, and then times 0.0391 liters per mole. So the mole unit cancels. Let's actually calculate this real quick here. I just want to see what this is equal to, because this is like the free space volume in the denominator. So the 0.6, if I do 0.6 minus 5.5 times 0.0391, my free space volume is 0.385. So you can see the gas particles are definitely taking up a negligible portion of this container at this high pressure. Let me actually carry out this arithmetic here. So like if we only corrected the free space volume problem, then you might say, well, what would the pressure be? Well, I take 5.5 times the gas constant times 298 Kelvin, and then divide by that volume. So that gives me 349 ATM. See how the pressure went up from where we calculated with the ideal gas law because the free space volume is smaller. So correcting the free space volume corrects this pressure here to be higher, but then we have to subtract the n squared a divided by v squared part. So we go back to 5.50 mole squared times the a constant, so 1.39. And the units there are liters squared ATM per mole squared. And we divide this all by the volume, but we go back to the container, not free space. So we go back to the 600 milliliter container. So let's calculate this part here. So 5.5 squared times 1.39, and then divide by 0.6 squared. And then this gives me 117 ATM. So now this pressure here is the pressure being lost due to the particles sticking together. So this is the pressure that's being lost due to the intermolecular forces, due to the particles sticking together. And so the pressure increases due to the free space problem being fixed, and then the pressure is being reduced due to the particles sticking together. And then when we do this arithmetic, 349 minus 117, we get 232 ATM. So a lot of work to calculate a better prediction of the true pressure, but this is going to vary a lot. If we did 2.5 to 3.5 to 4.5 to 5.5 to 6.5 moles, you're going to get a wide range of differences between your van der Waals pressure and the ideal gas law pressure. They're pretty similar here, but if we go down a little bit, we're probably going to get a worse prediction with the ideal gas law. If we go higher, we're going to get presumably even worse. And so what we can see here is that the van der Waals pressure is trying to correct for the intermolecular force problem, and it's trying to correct for the free space problem. And so the van der Waals pressure, again, is just a better prediction of the true pressure of a gas mixture. So big equation, but we just plug into it and solve for the pressure that it gives us. And so the last slide, I think I'll just mention this problem in passing, and maybe we'll work on this on one of our review days. But this problem here is just looking at generating a gas, but where we're collecting the gas over water. And so because we're collecting the gas over water, we have to work out and see how much of the pressure is that water vapor has. So whenever we're decomposing and forming so much gas here, that the pressure of our gas here is due to the pressure of the oxygens being generated in our reaction, plus the water vapor pressure. So I think we'll revisit this problem later when we get to like a review day. So let's come back and look at this problem another day. And so we'll just end it here today, and we'll pick up with chapter 11 on Wednesday. Chapter 11 gets into liquids, so once gases begin to experience intermolecular forces, they liquefy. So we'll talk liquids in chapter 11 next time. All right, guys, have a great day.